Math 2414, volumes. Volume of a solid of revolution. The washer method, example 1. Find the volume of the solid obtained by rotating the following lamina around the x-axis. Our lamina is bounded above by the equation y equals 3x and bounded below by the equation y equals x squared, And we're going to rotate this around the x-axis. Now, do you notice the main difference between this solid of revolution problem and the previous two? The main difference is, on this one, the axis of rotation, the x-axis, is not a boundary of the lamina. Remember the previous two, we had something like this, and we run around the x-axis, which was the boundary of the lamina, and then we had something like this, and we went around the y-axis, which was the boundary of the lamina. Now, why is that important? Well, when we rotated around an axis that also served as a boundary of the lamina, the cross-section was a circle. But when the axis of rotation is not a boundary of the lamina, that means there is a gap between the axis of rotation and the bottom of the lamina. Now, why does this matter? Because when we spin this around, our cross-section is not going to be a circle. Let's see if I can draw this. If I spin it around, it's going to look a little something like that. It's almost going to look like an ice cream cone, but the insides of it are kind of curvy. But what would it look like if we picked a point on the x-axis, shade in the bottom half of this, and we took a cross-section, which would have a gap in the middle. We took this cross-section and spun it around. Do you know what shape we would get? We wouldn't get a circle. We would get a circle with a circle removed from the middle of it. In other words, if we took this real skinny piece of this lamina here and spun it around the x-axis, we would get a shape that looks like, let's get rid of this. We would get a shape that looks like this. Spin it around and we get this shape. A circle with a missing circle in the middle. This is called a washer, for those of you who have ever used washers. So if we can figure out the area of this washer, then we can just integrate it. But how do you find the area of a washer? Well, the area of a washer is just the big circle minus the little circle. For reference sake, let's say that the big circle has a radius of capital R. And so the area of the big circle would be pi capital R squared. And let's say that the radius of the whole, the interior circle, is a lowercase r. And so the area of the circle we would remove would be pi times little r squared. Okay, so we have the formula for the area of a washer. It's just a circle minus a circle. But we have to go back to the picture over here and ask ourselves, where is the big radius and where is the little radius in this picture before we rotate it? The big radius, remember the axis of rotation is right here. The big radius is the distance from the axis of rotation to the top of the lamina, meaning that the big radius is right there. If we cut this at some x value, on which graph does the big radius reside? And the answer is the one on the top. That means that this point up here on the graph of y equals 3x would be x, the x coordinate at which we cut the cross section, comma capital R, the outer radius of that washer. Where would the inner radius be? Well, the inner radius is the distance from the axis rotation to the bottom of the lamina. The distance from the axis of rotation to the bottom of the lamina. So we'll put a little r right there. The point involving the little radius is on the bottom boundary, so that point would be x comma little r. And now we got almost everything that we need. We want our area as a function of x. Right now it's a function of the two radii, but I know points on graphs that involve these radii. The larger radius, capital R, is the y-coordinate of the point on this graph, but this graph was y equals 3x, which means if we take this ordered pair and put it into that equation, the y-coordinate is capital R, the x-coordinate is just x, and we get that the outer radius at this x-coordinate is 3x. And similarly, down here, the ordered pair involving the inner radius, lowercase r, is this point x comma r, but it's on the graph of the bottom boundary, which was y equals x squared. And so if we take that ordered pair and put it to the equation of the bottom boundary, the y-coordinate is r, and the x-coordinate is x, and we get that the inner radius is r equals x squared. Now you might be thinking those are just the two functions whose graphs we had as boundaries, and you would be correct. Okay, so where are we? Here's where we are. We know that the outer radius is 3x, so pi big R squared becomes pi times the quantity 3x squared, minus pi times the inner radius squared, little r, but in this picture, little r is equal to x squared, so r squared becomes x squared squared. Let's clean this up. 3 squared is 9. We have a pi. X squared, of course, is x squared, minus pi. X squared squared is x to the fourth. And now we've got a formula for the area of that washer when we cut this solid at some x coordinate. All that remains now is to integrate the area over the correct interval of integration. But what is that? Well, the picture's kind of messy, so I'm going to quickly resketch the lamina over here, the top of which was y equals 3x, the bottom of which was y equals x squared. And we need to know what the x coordinates are that represent the intersection points. You're probably thinking this one is 0, and you would be correct. But to find the intersection points, we have to equate the functions and solve. Since at both intersection points, the y's have to be equal, we have to have x squared is equal to 3x. If we subtract 3x, we get x squared minus 3x is equal to 0. We can solve that by factoring. Factor out an x to get x times x minus 3 is equal to 0. This is just college algebra. And solve to get x equals 0 and x equals 3. Which you can inspect to make sure that those are correct. Squaring 0 and tripling 0 give the same answer, 0. Squaring 3 and tripling 3 give the same answer, 9. So those are the correct x values, which means we're ready to set up our integral. The integral from 0 to 3 of this guy, 9 pi x squared minus pi x to the fourth dx. Oh, this is calculus 1 problem now. Raise the power to 3, divide by 3, so we'll get 3 pi x cubed. And if you question that move, take the derivative and go, yep. Over here, we would raise the power to 5 and divide by 5, so we get 1/5 pi x to the fifth. And this is going from 0 to 3. All right, let's see what happens. Quick observation, the 0 does annihilate the antiderivative, so as a lower limit, I can ignore it. If it didn't annihilate the antiderivative, or if it were the upper limit, we couldn't do that. Speaking of upper limits, let's put in the 3. We get 3 pi times 3 cubed, minus 1/5 pi times 3 to the fifth. 3 cubed is 27, times 3 is 81, so we get 81 pi. 3 to the fifth is 243, times 1/5 is 243 fifths pi. These are like terms, so they should be combined, so we would need to get a common denominator of 5. If I multiply 81 times 5, I get 405. This one's already got a 5 in the denominator. So 405 fifths minus 243 fifths is something. Let's see, 405, 205, 202 minus 40 is 162. Let me add that to make sure. Yep, 162 fifths pi. Or you could write it as 162 pi with 5. Either one's okay. But to review, and this is the important part, if you're rotating a lamina around an axis of rotation, but the axis of rotation is not a boundary of the lamina, then your cross section will be a washer, one circle minus another. Now, if you wanted to try to generalize, it wouldn't be that hard, because look what we have right here. One circle minus another. The radius of the bigger circle was the equation of the top boundary, and the radius of the inner circle, the hole that was removed, was the equation of the bottom boundary. So we could do a real quick generalization by removing the specific functions. And this time, instead of writing it all out in words, I'm just going to give you the washer method. By the way, the washer method and the disk methods are both just specific cases of integrating the area. When you rotate something around an axis, you're going to get a disk or a washer, depending upon whether or not the axis of rotation is also a boundary. If it is, it's a disk. If it's not, it's a washer. So without further ado, if we have this lamina up in the sky, whose upper boundary is y equals f of x, and whose bottom boundary is y equals g of x, and we're going from A to B, and we rotate around the x-axis, then the volume is going to be the integral from A to B of pi times the square of the top function minus pi times the square of the bottom function. So pretty straightforward if you're going around the x-axis. What if we're going around the y-axis? Funny you should ask that.